Fraunhofer diffraction at single slit. Let us first complete the diagram. This straight line over here is plane wavefront, which we are denoting by W. So this W is plane wavefront of wavelength lambda, and there is a slit AB over here, and this AB is rectangular slit of width A. Width of the slit is A, and plane of slit is perpendicular to plane of paper. So the plane of the slit is perpendicular to the plane of the paper. If in this direction there is a plane of the slit, then in this direction there is a plane of the paper. So their planes are perpendicular to each other. Then what happens? This wavefront W incident on the slit. When this wavefront incident on slit, every point in the plane of the slit acts as a secondary source and emits secondary waves in all directions. This is as per Huygens wave theory of light. So according to the Huygens theory, every point in plane of slit acts as secondary source and emits secondary wave in all directions. That is as per Huygens theory of the light. When this wavefront W incident on this slit, then every point in this plane of the slit acts as a secondary source and it emits secondary waves in all directions. That is as per Huygens theory. Then let's say that the secondary waves which are normal to the plane of the slit, these secondary waves which I have shown over here, these secondary waves are normal to the plane of the slit and they are brought to focus on the screen, let's say at point P0. So all secondary waves which are normal to the plane of the slit are brought to focus at point P0. Let us say this is point P0. So our point P0 is the point where all secondary waves which are traveling normally to the plane of the slit, or all secondary waves normal to plane of slit, are brought to focus at point P0. Then what would be the intensity at point P0? So all secondary waves which are reaching at point P naught, they are traveling same distance. All secondary waves which are normal to plane of slit are traveling same distance to reach at point P naught. So those secondary waves which are focused at point P naught are traveling same distance from the plane of the slit. And, and that's why they are having same phase. There will not be any path difference between the secondary waves which are reaching at point P naught, because all these waves are traveling same distance to reach at point P naught, so there won't be any path difference. In other words, all these secondary waves are having same phase at point P naught, and hence intensity at point is maximum, and we are calling it central maxima. So intensity at point P naught is maximum, and we are calling that point as central maxima. In case of the interference, we say there is a constructive interference and there is a destructive interference. But in case of diffraction, we say maxima or minima. So in this case, at point P naught over here, we are getting the central maxima. Then we will consider one more point on the screen, which is all secondary waves which are making an angle theta with normal to the plane of the slit. So these are the secondary waves which are making an angle theta with normal to the plane of the slit. In this case, normal to the plane of the slit is this direction. So all those secondary waves which are normal, which are making an angle theta with normal to the plane of the slit, they are brought to focus on the screen, say at point P1 over here. So we are going to consider only 2 points on the screen, point P1 and point P0. So let us see what is the point P1. So in case of point P1, we can say that all secondary waves which are making an angle theta with normal to plane of slit are brought to focus at point P1. Then what would be the intensity at point P1? So intensity at point P1, because all those secondary waves which are reaching at point P1, they are now traveling different path to reach at point P1. All these secondary waves which are reaching at point P1, they are traveling different path, and hence intensity at point P1 depends on the path difference between them. So we can say that intensity at point P1 depends on path difference between secondary waves which are reaching at point P1. So its intensity depends on point P1. The intensity at point P1 depends on the path difference between all secondary waves which are reaching at point P1. Now to find out that, let us make the assumption. Let us assume that now when this wavefront incident on the slit AB, every point in the plane of the slit acts as a secondary source. So there can be numerous secondary sources in the plane of the slit. But for convenience, let us say this is our slit AB, and for convenience, we are going to assume that there are only 10 point sources. So what we are assuming here, our assumption is, suppose there are 10 point sources in slit AB. So see, this slit AB is divided into, let's say, two halves. Slit AB is divided into two halves. So this is, say, the midpoint AO and OB. AO and OB. And total, there are 10 point sources. So source 1 to 5 are in upper half. Slit AB. Upper half of slit AB. That is in the region AO. And source 6 to 10 are in lower half of slit AB. That is OB. So in OB there are 5 point sources, and in AO also there are 5 point secondary sources. Let's show that in this diagram. Here there is number 1 source, number 2, number 3, number 4, and number 5. So these are the 5 sources in the upper half of the slit AB, and this is, let's say, 6 7, 8, 9 and 10. So this is the source 6 and this is the source 10. This is source 1 here and this is source 5 over here. So this is our assumption. What is our assumption? That slit AB is divided into two halves. In the first half, there are 5-point sources, and in the next half, there are 5-point sources. That is our assumption. Now here, look at this diagram. The source 1 and source 6. Point source 1 and 6. Separated by distance a by 2, as you can see here. Separated by distance a by 2. As you know that the total distance is a. This one is a. But the distance between the source 1 and the source 6, this distance is a by 2. Similarly, the distance between the source 2 and source, this is source 2 here and this is source 7 here. So distance between the source 2 and 7 is also a by 2. Between 3 and 8 is also a by 2. Then what would be the path difference between secondary waves which are emitted from the source 1 and source 6? We are considering secondary waves which are emitted from source 1 and the source 6 at an angle theta with normal to the plane of the slit. Then what would be the path difference between these two secondary waves? This is the first secondary waves which is emitted from the source 1 and this is the second secondary waves which is emitted from the source 6 at an angle theta with normal to the plane of the slit. Then how much would be the path difference between this secondary wave 1 and 2 emitted from the source 1 and 6? To find out that path difference, we have to draw normal on this secondary waves and this angle is theta. This distance from here to here, that is the distance between the source 1 and 6, is a by 2, and therefore the path difference between these two waves is this. This is the path difference. And from the figure, we can conclude that path difference is nothing but a by 2 sine theta. So here, source 1 and 6 separated by distance a by 2, and the path difference between secondary waves emitted from source 1 and 6 is a by 2 sine theta. So we got the path difference between the secondary waves emitted from source 1 and 6. Similarly, we can find the path difference between path difference between secondary waves emitted from source 2 and 7, source 3 and 8, source 4 and 9, and source 5 and 10 has path difference a by 2 sine theta. So in this case, what we are considering is one secondary waves from the upper half of slit AB and the another secondary wave is from the lower half of this slit. So secondary waves emitted from source 1 and source 6. The path difference between them is a by 2 sine theta. Similarly, secondary waves emitted from the source 2 and source 7 is also a by 2 sine theta. Secondary waves emitted from source 3 and source 8 is also a by 2 sine theta. Let us assume that at the point P1, here at point P1, these secondary waves which are making an angle theta with normal to the plane of the slit are reaching at point P1. And let us assume that at P1 we get the first minima. So for first minima, we know that the path difference is a by 2 sine theta. And when this path difference a by 2 sine theta is equals to lambda by 2, we will get the first minima. This equation we can write as a sine theta is equals to lambda. So this is the equation for the first minima. Let us generalize this equation. We can write this as a sine theta is equals to m lambda. In this case, m is plus minus 1, 2, 3, etc. So we get the equation for the minima. When a sine theta is equals to m lambda, we get the minima. But this equation a sine theta is equals to m lambda tells nothing about the intensity of the light variation on the screen, because here, as we have studied in the difference between interference and the diffraction. Interference fringes are sharp fringes. Their dark fringes are completely dark, bright fringes are completely bright. But in case of the diffraction fringes, which we will get on the screen, the dark fringes are not completely dark. There is an intensity variation. No uniform darkness for the dark fringes or no uniform brightness for the bright fringes. For example, on the screen, what we will get is the fringes like this. These are the diffraction fringes. So here we can see that this is at this point we get the central maxima. At the center, you can see here this arrow shows the amplitude and or electric field, and this arrow, the length of this arrow is maximum at the center, and so at the center you will get the maximum intensity. But as you go away from the center, from here in this direction or in this direction, intensity of that central maxima decreases. It goes on decreasing in this way, and at this point there is a minimum intensity. At this point, which is our point Even the intensity is minimum. But if you go on either side of this minimum intensity, this side or this side, intensity is not minimum. So you can say that the dark fringe is not completely dark. And now what we got is the equation for the minima, which is a sine theta is equals to m lambda. This equation gives us the angle of diffraction theta, that is in which direction we'll get the minima, that is a minimum intensity. But there is a variation in the intensity that we cannot find out using this relation. And that's why to find out intensity distribution, we are going to follow graphical path. Let us see what is this new phenomena to find intensity distribution on the screen using the graphical path. Now we have a slit AB. This slit AB, let us assume that slit AB is divided into n number of small slits. We are assuming that it's not a single slit of width A. We are assuming that in that slit A of width A, there are n number of small slits, each slit having width dx. So there are n number of slits in slit AB. There are n number of small slits. Each one is having width dx. And therefore you can write this like A, which is the width of the slit AB, and that is equals to width of the slit 1 plus width of the slit 2 plus up to the width of the slit n. So we are assuming that there are n number of small slits, and every slit now acts as a secondary source. There are n number of slits in, suppose this is our slit AB, and in this AB, whose width is A, width of this slit is A. But now in this slit, there are n number of small slits. Each one is having equal width equals to dx. And each slit acts as secondary source and emit secondary wave. Each slit acts as a secondary source and emit secondary waves, which are represented by phasor. The new concept, the phasor. What is phasor? Phasor is quantity having phase and magnitude. Just like a vector. Vector has direction and magnitude. Our phasor has phase and magnitude. So from each slit, we can say now instead of saying that each slit acts as a secondary source and emits secondary waves, we are saying that each slit acts as a source and emit phasors in all directions. So for simplicity, we are assuming that length of phasor, that is its magnitude, is delta E, coming out from each slit. That means the each slit emit one phasor of length delta E, and adjacent phasors are out of phase by delta phi. Okay, each phasor which is emitted from the small slit having magnitude delta E, and the phase difference between the adjacent phasor is delta phi. Then let us find out the path difference between the adjacent phasors. For that, let us consider the two slits here. We are considering two slits. Let us say this is slit 1 and this is slit 2. Now each slit emit one phasor from the center of the slit. One phasor is emitted in each direction from the center of the slit. Let us write that. One phasor emitted by slit in particular direction. So every direction, it means that one phasor is emitted. Now these two phasors are emitted from the adjacent slit, and the width of each slit is dx. So the distance between the center of these two adjacent slits is dx. And of course this angle is theta. And we have to find the path difference between these two phases. To find the path difference between the phasors, we have to draw the normal to this second phasor, and the distance from this point to this point is path difference. As you see here, this angle is theta. The distance between these two centers is dx, and so this distance, that is the path difference between the two adjacent phasors, is dx sine theta. So path difference is equals to dx sine theta. If this is the path difference, then corresponding path difference, corresponding phase difference is, let's say, delta phi between the adjacent phasors, which is equals to 2 pi by lambda dx sine theta. So we have the path difference dx sine theta, and corresponding phase difference is 2 pi by lambda dx sine theta. This is the graphical method. And by using this method, we will find what would be the intensity at point P0 or any other point on the screen. Now let's go back and consider the point P0. So at point P naught, how many phasors are reaching at point P naught? As you can see here, this is our point P naught. Now at point P naught, all secondary waves which are normal to the plane of the slit are brought to focus at point P naught. Now we assume that in this slit AB, there are n number of small slits, and each slit emit one phasor in particular direction. So how many phasors are reaching at point P naught? Obviously, there are n number of phasors which are reaching at point P naught. But the angle between the adjacent phasors is zero. Angle theta, because all those secondary waves which are making an angle zero, they are reaching at point P naught. So the angle, that is theta, between secondary waves, between secondary phasors, is zero. And n number of phasors are reaching at point P naught. So these n number of phasors lies end to end, as all phasors are meeting at phase, so they are having the same phase. There is no phase difference between the waves which are reaching at point P naught, and that's why these phases will lie end to end. So what would be the total electric field at point P naught? So at point P naught, let us say this is the one phasor whose amplitude is delta E, emitted by the first slit. Then this is the second phasor. His amplitude is also delta E. And the angle between the first and second phasor is zero. Theta is zero. These two phasors are in phase. They are meeting in phase. So these phasors, when they are reaching at point P naught, they lies end to end, and the resultant, or the total electric field, at point P naught is equals to n times delta E. N phases of magnitude delta E arriving at point P naught. So we get n times delta E, and this electric field at point P naught is maximum, and that point P naught is the center point over here. This is the center point. So at this center point, the intensity is maximum. Then at this point, let us consider at this point or this point. So those secondary waves which are reaching other than point P naught, maybe here, 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 here. So they are reaching at point other than P naught, will be having some phase difference between them. These secondary waves will not make an angle zero with normal to the plane of the slit. They will make some angle to reach the next point, maybe at this point. Then what would be the intensity and how to calculate intensity at that point? So since these phasors are making some angle, let us say this is the first phasor over here. Magnitude of that one is delta E, and this one is the second phasor. And let's say the phase difference between these two phasors is delta phi. So there is some angle between these two phasors. There is some phase difference. So since there is some phase difference, these n number of phasors which are reaching on the screen other than point P naught will form a arc. That will not be the straight line, because you will get the straight line when angle is 0. But now it's not a straight line. There is some phase difference. There is some angle between the phasors which are reaching at point other than P naught. And so this is it form an arc of length EM. And the resultant of this arc, we have to draw the chord just like the vector sum, vector addition, or this is the phase addition. To find the resultant electric field, we have to draw chord. This one is chord, which is, let us say, ER, resultant electric field. Now when there is zero angle, this length would be equals to EM, which is the maximum electric field. But now if there is some angle between the phasors, then resultant ER would be less than EM. Certainly, ER, that is the length of the chord, is certainly less than the length of arc. So ER is less than EM. Then total phase difference would be, that is the phase difference between this phasor and this phasor. That is the total phase difference would be, let us say, phi, and that would be equals to n times delta phi, as the phase difference between the adjacent phasors is delta phi, and there are n number of phasors. So the total phase difference phi is equals to n times delta phi. And we know the value of delta phi. Just now we saw what is the value of delta phi over here. This delta phi, which is equals to 2 pi by lambda dx sine theta. So this is into 2 pi by lambda dx sine theta. That is equals to 2 pi by lambda a sine theta, as a is equals to n time dx. So we got the total phase difference 2 pi by lambda a sine theta. Now if you increase the theta further, now there is a phase difference of this delta phi. If the phase difference increases, that is the angle theta, this theta increases. So we are moving from this point to this point over here. As the theta increases, we will get the points over here and here. And as you can clearly see that as the theta increases, this curvature of the arc will become more and more curved, and the length of the chord will decrease. And so in this case, the intensity decreases as the length of the chord decreases. So as theta is increased further, at certain angle, this chain of phasors will form a closed path. We are increasing the theta. As we are increasing the theta, the chain of phasors will form a closed path like this. This This arc will become more and more curved, and then at certain angle theta we will get the circle. So as theta increases, this chain of phases formed closed path. That is, all these phases are lying on the circumference of this circle. So they will form a closed path. And at this point, vector sum of phases is 0. At this theta, vector sum of phases is 0. That is, ER is equals to 0. And this corresponds to first minima. This corresponds to first minima on screen. So what would be then total phase difference? Phi is equals to n times delta phi, and that is equals to 2 pi, that is a 2 pi for the circle, which is equals to n times delta phi is 2 pi by lambda dx sine theta is equals to 2 pi. This 2 pi cancels with this 2 pi. N times dx is a sine theta. So we can write a sine theta is equals to lambda. And this is the equation for the first minima. A sine theta is equals to lambda. So first minima occurs in the diffraction pattern when a sine theta is equals to lambda, or sine theta is equals to lambda upon A. And these things goes on repeating, just like the spring in the watch. If you tight it, you get the first circle, second circle, and third circle, like that. So the first circle means the first minima. If you get the second circle, that is, if you tighten these phases further, there will be the second layer like this. You will get the second circle. There you will get the second minima, and so on. So this is the graphical method to calculate distribution of the intensity of the diffraction pattern. Now let us find total electric field and intensity at any point on the screen. We will derive now equation for total electric field, say electric field ER, and intensity IR at any point on the screen. And to find that, we are considering limiting case. The limiting case is as dx becomes infinitesimal as n approaches to 0. Dx becomes infinitesimal as n approaches to 0. And let us consider that these phasors follow arc of circle of radius. At this point, these phasors, there are n number of phasors on this arc, and this arc is a, a part of the circle of radius r. So what we are considering here, that phasors follow arc of circle of radius r. whose center is C. So let us say that this is C. C is the center of the circle of which this arc is a part. So, and the radius of that is R. So let us join. Let us say that this point is A, this point is B, and I am joining point A with the center of the circle of which this arc is the part. And so the distance CB is nothing but the radius of that circle. Similarly, AC is also a radius of that circle. So on this arc, there are n number of phases lying one after another, and the phase difference between the adjacent phases is delta phi. And the resultant of this phasor is the chord. So this is the chord. And let us say the length of the chord is ER and the length of arc is EM. Then I am drawing the line, let's say CM. This is the line CM, which I am extending it further. Let's say this point is M. And I am also drawing a tangent at point A, and from point B. Let's say this point is O. In this case, CM is perpendicular to AB. We are extending CM. This is the M point over here. CM extended to intersect two tangents lines AO and BO at point O. So that this is the point O over here. As you can see in this diagram, this ACB is isosceles triangle. As you know, you can see that in this case, this AC is equals to CB, and that is equals to R, and also AM is equals to MB. So this chord here, the chord ER, is divided into two parts, two equal parts. This is ER by 2, that is AM, and this is MB, which is also equals to ER by 2. And so this ACB is isosceles triangles, and this also conclude that this AOB also isosceles triangle. And this angle here is phi, and as you can see the total phase difference, we know that from A to B, the total phase difference, that is this total angle, is equals to phi. This, and so this angle is also equals to phi. Let us describe this diagram further. As you can see here, what is EM here? EM is length of arc. Then there is a ER. ER is length of chord. As you can see here, the angle ACB is equals to phi, and angle ACM is equals to angle BCM, and that is equals to phi by 2. And let us assume that this phi by 2 is equals to alpha. Assume phi by 2 is equals to alpha, which is, we know phi. Phi is 2 pi by lambda a sin theta. Now here is phi by 2. So this phi by 2 is equals to pi by lambda a sin theta, and that is equals to alpha. We are assuming phi by 2 is equals to alpha. Then from figure, what would be sine phi by 2? As this total angle is phi, so this one is phi by 2, and this is also phi by 2. So what would be sine phi by 2? So sine phi by 2 is equals to ER upon 2R, or the resultant electric field ER is equals to 2R sine phi by 2. Let us say this is our equation 1. Now we know the relation between the angle, arc and the radius. We know that angle is equals to arc upon radius. In this case, angle is phi. Arc length of arc is EM, and radius is R. From this, we get R is equals to EM upon 2. This is our equation 2. Then let us substitute equation 2 in equation 1. So we get then this ER is equals to 2EM, just a minute, for this is phi. So ER is equals to 2EM upon phi into sin phi by 2. This I can rewrite as EM sin phi by 2 upon phi by 2. But phi by 2 we assume equals to alpha, and that's why ER is equals to EM sin alpha upon alpha. And this equation gives us resultant electric field at any point on screen. So in this, using this equation, we can find out what would be the resultant electric field on the screen at any particular point. And we know that what is the relation between the intensity and the amplitude, that is electric field. So if IR is resultant intensity and IM is maximum intensity, then from this equation we can write resultant intensity IR is equals to Im sine square alpha upon alpha square. So this equation gives us resultant intensity at any point on screen. So we got, the equation for resultant electric field, or you can say resultant amplitude, as well as equation for the resultant intensity at any point on the screen. So let's find then the condition for principal maxima, that is the point P naught. The condition for principal maxima. To find the condition for principal maxima, we have the relation for resultant electric field is equals to Em sin alpha upon alpha. Now I want to rewrite this equation of Er as Em upon alpha, and into bracket I want to write sine series. So sine alpha series is alpha minus alpha cube upon 3 factorial plus alpha raised to 5 upon 5 factorial minus and so on. I want to take alpha common here. So alpha I can take common. That alpha will cancel with this alpha, and I will get Em into bracket 1 minus alpha square upon 3 factorial plus alpha raised to 4 upon 5 factorial minus and so on. And we know that at the point P naught we get the maxima. We want maximum electric field. So here this Er should be maximum for the principal maxima or the central maxima, and for this Er to be maximum, alpha should be 0. But we know alpha. This alpha is nothing but pi by lambda a sine theta. Now pi lambda a cannot be 0. So sine theta should be 0 to get alpha equals to 0. So this should be 0, and for that sine theta should be 0. And you get sine theta equals to 0 when theta is equals to 0. And in that case, maximum value of Er is Em when theta is equals to 0. So when alpha is 0, that is when theta is equals to 0, you get Er equals to Em, and this is called principal maxima. Okay, so we got the condition for the principal maxima, that is theta should be 0. Then let's find minimum intensity position, that is minima. To find the minimum intensity position, consider the equation for the intensity. So we have here in this case Ir is equals to Im sine square alpha upon alpha square. And we are finding the minimum intensity position. So we get Ir is minimum when sine alpha is equals to 0. So sine alpha should be 0 to get the minimum resultant intensity. That means the alpha, which is equals to pi by lambda a sine theta, and this should be equals to plus minus m pi, where m starts from 1, 2, 3, etc. plus minus. So when this alpha is plus minus m pi, you get sine alpha 0. And when sine alpha is 0, the intensity is minimum. So let us simplify this equation. This pi cancels with this pi, and what you get is a sine theta is equals to plus minus m lambda. The plus minus m lambda is because on either side of principal maxima, we get points of minimum intensity. So there you get the minimum intensity positions, and this is the equation for minimum intensity position. Then let's find secondary maxima, positions of secondary maxima. To get the position, we get weak secondary maxima exactly between two minimas. We get weak secondary maxima exactly between two minimas. As you can see here in this diagram, these are the minimas. So these minimas are exactly, these secondary maxima are exactly between the two minimas. This is a minima, this is minima, and exactly in between these minimas, we get this secondary maxima. And hence we can find out this secondary maxima by differentiating the intensity equation with respect to alpha and equals it to 0. These positions here, this maxima, secondary maxima positions obtained by differentiating intensity relation with respect to alpha and equating it to 0. So we have the intensity equation here, which is IR equals to Im sine square alpha upon alpha square. Now let us differentiate this with respect to alpha. So d of IR by d alpha is equals to Im 2 sine alpha upon alpha into bracket alpha cos alpha minus sine alpha upon alpha square. So this is the differentiation of resultant intensity with respect to alpha. Now this should be 0. To get this 0, sin alpha either sin alpha should be 0 or alpha cos alpha minus sin alpha should be 0. Either this should be 0 sin alpha or this should be 0. But this cannot be 0 because when sin alpha is equals to 0, we get minimum intensity. And therefore, this alpha cos alpha minus sin alpha should be 0. We can simplify this and we get alpha is equals to tan alpha. Now this equation we cannot solve directly. To solve this equation, we have to plot a graph which is equals to, we have to consider y is equals to alpha and y is equals to tan alpha. So we have to plot a graph of y equals to alpha and y equals to tan alpha to get the values of alpha. So the graph, suppose this is x-axis, this is y-axis, this is y-axis, then y equals to alpha, we get the straight line. This is y equals to alpha. Then y equals to tan alpha, alpha will be having different values. Then we get this is y equals to tan alpha when alpha is 0, and we'll get this is y equals to tan alpha when this alpha is 3 pi by 2. This is alpha over here. Then also again this is equals to 5 pi by 2. Similarly, you will get this side also. This is minus 3 pi by 2 and this is minus 5 pi by 2. So these are the intersection values. We get the value of alpha at these intersections. That is when this alpha is equals to 0 or that is equals to this is here, this value over here 3 pi by 2. So when alpha equals to 0 or plus minus 3 pi by 2 or plus minus pi by 2, we get the secondary maxima. So that we can write that this A sine theta is equals to plus minus 2n plus 1 lambda by 2. We will get this equation. So by putting the value of alpha is equals to plus minus 2n plus 1 pi by 2. In terms of phase difference, this is in terms of path difference. So this is the equation for the path difference for the or these are the points where you get the secondary maxima.